Welcome back. In the last session, we proved in Theorem 1 that any ring R without multiplicative identity can be embedded in a ring S, where S is defined as the Cartesian product of R and the ring of integers, and S is with multiplicative identity. We also shown that if R is commutative, then S must be also commutative. So at least one property is preserved in S. However, this construction of S does not preserve all important properties. For example, if R is with no zero divisors, then it is not necessarily the case that S must be with no zero divisors. And to see this, let's take a simple example of the ring of even integers. Obviously, this ring is with no zero divisors because if any A and B in R where both are not zero, then their product cannot be zero. Okay. Now we can show that the ring S, where S of course is R cross Z, can be with zero divisors. So let's take example 2 elements, minus 2 and 2, and then 2 and 0. Okay, both are in S. Now what is their product? According to the multiplication formula which we defined, remember that AM times BN equal AB plus NA then plus MB. Okay, and finally here we have MN. Okay, so if we apply this, we obtain minus 4 here plus 0 times minus 2, we just 0, plus 4. Okay, and here is 0 times 2, so 0, and this gives us 0 and 0. Of course, this is the 0 of R, and this is the 0 of Z. So we have a case of two non-zero elements in S where their product is 0. So S does not preserve the property of having no zero divisors. However, we can build on S to provide a solution of embedding R in a ring such that the new ring is with no zero divisors, and this will be the subject of the next theorem. So theorem 2, and it goes as follows. Okay, any commutative ring R with no zero divisors can be embedded, okay, in an integral domain. Remember that integral domain is a ring with multiplicative identity, and it is commutative and with no zero divisors. Okay, so what is the proof? Let's start from our ring S. Okay, so let S equal R cross Z. Therefore, S must be with identity element, and S is commutative. Okay. Now let's define the following set. So let A equal all Z in S. Okay, such that Z times A equals 0 for all A in R. Remember that R can be viewed as an ideal of S, okay? By the embedding theorem of the first session, R is embedded as an ideal. So this element A here is in fact the element A and 0 of the ordered pair when viewed inside S. Okay. This set is called the annihilator of R in S. So it annihilates all the elements of R, making them all 0. Okay. Now we will proceed as follows. First, we will prove that A is an ideal of S. Okay. And this will allow us to define the quotient ring S by A, because for the quotient ring to be defined, this A here must be an ideal. Okay, so S by A can be proved to be an integral domain. Okay, then we can show that R can be embedded into S mod A. Okay, so this is the steps of the proof which we are going to carry now. Okay, first, the first claim, A is an ideal of S. Okay, A is an ideal of S. So we proceed. First, we need to prove that A is non-empty. Okay, but this is clear since 0, of course 0R, and 0Z is in A, because the product of this 0 by any elements from R is necessarily 0, then A is non-empty. Okay, and second, we need to prove that for any Z1 and Z2 in A, then Z1 minus Z2 must be also in A. Okay, and for this we note the first that for any Z1 equal AM, if we take this definition of Z1, and Z2 let it be Bn, then their product AM by any element of R must be, the product of any element of R must be 0. Okay, so if we take the product with R0, this is an element of the ideal R of S. Okay, this must be 0 and 0, and this implies that AR, so we take this product here, plus 0A plus MR and 0 equal 0 and 0. Okay, therefore AR plus MR must be 0. Okay, so this is equation 1, and similarly Bn times R0 must be 0. Okay, and this means that BR plus 0B plus NR and 0 equal 0, 0, which implies that BR plus NR equal 0. Okay, so this is 2, and let me take these two equations here. So we have we have AR plus MR equals 0, 1, and 2 we have BR plus NR equals 0. Okay, so this is 2. Now we take Z1 minus Z2. Note first that Z1 minus Z2 equal AM minus BN, and this by the definition of addition equal A minus B and M minus N. Okay, now we take the product of this difference with the element of R. So Z1 minus Z2 times R0. Okay, and this equal Z1, where Z1 is A minus B, M minus N. This is Z1 minus Z2 times R0. Okay, and by multiplication, this equal A minus B times R plus, of course, 0 times A minus B, so we can skip it, plus M minus N times R and 0. Okay, and this in itself equal, so here AR minus BR plus MR minus NR, again with 0. So rearranging, we obtain this is AR plus MR minus, so this is here, BR plus NR, okay, and 0. Now from 1 here, we have AR plus MR equals 0, so this is 0. And from 2 we have BR plus NR equal 0. So this gives us 0 and 0. So this means that Z1 minus Z2 is in fact an element of A. This proves the second requirement of being an ideal. Now we check the third requirement, which is multiplication by elements from S. Okay. So what we want Z1 dot any element from S, let's say CK, to be in A. Okay, where of course CK is just a random element in S. So let's verify this. We have Z1 of course equal AM, then we have here CK, and by the multiplication formula this equal AC plus KA and plus MC, and here we have KM. Okay, so this is 1. On the other hand, we have AM times C0. C0 is an element of R because all the elements of R are in this form. So since Z1 is in A, this must equal 0, of course. But this in itself equal AC plus 0A. Okay, so it's just 0, so we can skip it. Plus, then we have MC. Okay, and then here, of course, we have 0. This equal 0, 0. This is 2. Now, by just comparing 1 and 2, we have AC plus MC course AC plus MC equal 0 from here. So we have AC plus MC equal 0, right? So this means that Z1 dot CK equal KA and KM, okay? And therefore we can take this K out here, and we have here AM. But AM is in A, and the product of AM, of course, with any element of R is 0. So this means this belongs to A, okay? It belongs to A because we can take the product of any element with this product, it will be 0. And this completes the proof that A is an ideal of S, okay? Now S mod A is defined, this quotient ring become defined. Now let's move to the next step. We want to show that S mod A is an integral domain, okay? All right, so we already know that this quotient ring is commutative because S is commutative, and this quotient ring is also with identity because S is with multiplicative identity. So only one thing remaining to prove that it is an integral domain is to show that this quotient ring is without any zero divisors, okay? So let's assume, okay, assume that we have two elements, B plus A and C plus A in the quotient ring S mod A, okay, such that their product is 0. So B plus A and C plus A, their product is 0 of the quotient ring, okay? And what is, of course, this 0 of the quotient ring is just 0 plus A, or we can simply write it A, okay? This is, of course, 0 of S. Now, what is the product here? This implies that BC plus A equals 0, okay? Which means that BC belong to A, okay, to the ideal A. And the A is the annihilator of R, which means for any element little r in R, we should have BC times R equal 0, okay? This is for all little r in R. Now, let's assume that this element is not 0, okay? So suppose that C plus A does not equal 0 plus A. This is the 0 element of the quotient ring S mod A, okay? And this in itself implies that C cannot be in A. And now what we are going to show is that this assumption will imply that B plus A is 0, which in turn means that S mod A is a ring with no zero divisors, because the product of any two elements equals 0 necessarily means that one of the elements must be the 0 element. Now, since C is not in A, it means there's at least one element in the ring R that is not annihilated by C. So this implies that exists some element, let's say little r, in R, such that CR is not 0. Okay? But R itself can be viewed as an ideal of the ring S. So the ring R, since R is an ideal of S, then the product by any element from S must be again in R. Okay? Then CR must be in the ring R. Now, for all elements R prime in R, we also have the product by elements from S in R. And in particular, we have the product BR prime must be in the ring R. Okay. Now let's take the product of these two elements. Okay. CR dot BR prime. Okay. This equal CR B with R prime. And since R is commutative, this will equal BC R then with R prime. But we have shown that BC is in fact an element of A. So it annihilates any elements of R. So this equal 0 dot R prime, which is 0. Okay. Now both CR and BR prime are elements of R. Therefore, their product must be in R. And we stated in the theorem that R is with no 0 divisors. And since this product equals 0, then one of the two elements must be 0. We have already shown that CR cannot be 0, and therefore we must have BR prime equal 0. Again, R is without 0 divisors, and R prime is any element in R. So we must have, in this case, B equals 0. Now, this means that B plus A here must be 0. Okay? So this means that B plus A must equal 0 plus A. Okay? And this shows that the quotient ring S mod A is an integral domain. Okay. Now one thing remaining is to show that R actually embeds into S mod A. Okay. And for this purpose, of course, we will need to define an injective homomorphism from R into S mod A. Okay, so let's define F from R into S mod A by F of R equal R plus A, but R equal R0, okay, viewed inside S. So this equal R0 plus A. Okay. Now first we show that this is homomorphism. So we have F of R1 plus R2. This equal R1 plus R2 0 plus A. And by definition of addition, this equal R1 0 plus R2 0 plus A, okay, which is equal R1 plus 0 plus A plus R2 0 plus A, okay, and this is specifically is R1 plus F R2. So second, we show the multiplication. So F of R1 R2, this is equal R1 R2 0 plus A, okay, and by the definition of multiplication, this can be seen to be equal R1 0 times R2 0, okay, and then plus A, okay, and this from the basics of the quotient rings equal R1 0 plus A, then times R2 0 plus A, okay, and this is precisely F of R1 times F of R2. So this implies that F is a homomorphism, okay. Now remaining to show is that F is injective, and as you know, this is equivalent to the kernel of F being the zero element. So let's examine the kernel of F, which is all elements letter R in R, such that F of R maps to the zero element of the quotient ring, which is 0 plus A. We can write it just A, okay, and this equal all R in R, such that by the definition of F we have here R0 plus A equal A, okay, so this equal R in R such that this element is R, okay, so we have R also in A, and these sets represent the intersection of the ring R with A, okay. Of course, R here is viewed as ideal in the ring S. Now we want to show, claim that R intersection A is 0, okay. So let's assume we have some element in this intersection, okay. Then since this element of course is in A, this implies that AR equals 0 for all little r in R, because A is an annihilator, so it annihilates all the elements of R, okay. But R is with no zero divisors, okay. So this implies that A must be 0, okay. So this shows that R intersection A is only 0, which means F is injective. And therefore F defines an embedding of R into the integral domain S mod A, okay. This brings us to the end of this session, and in the next session we will take things a step further and show that every integral domain can be embedded into a field.